Okay, so today we have example 2 and 3 from chapter 3. That's really, I think that's all you need, but usually people, they get into those vector homework problems and they start to ask, oh, maybe we need one more example or something. So I usually make up one or two to close out this week. So if you didn't see example 1 yet or you forgot all about it, you should flip back there and check it out. It's the soccer kick, 20 meters per second at 30 degrees above horizontal. That was the last example. And then it hits something at 1.5 seconds. Well, now, example 2 is what if it doesn't hit that post? What if it just falls back and hits the ground at delta y equals 0? Okay, so, okay, and we're going to calculate the maximum range. And we're going to call that capital R of this kick. So let's see, I am going to, this time, use algebra. We'll see how you feel about that. I'm going to use just algebra and plug in numbers at the end. Okay? Oh, yeah, let's write that. Okay, so my capital R is the maximum range, that's delta x max. Okay, it's worth writing that down once. From now on, we'll just use capital R. Okay, that amount is going to be equal to v0 cosine theta. Theta is my 30 degrees, v0 is 20 meters per second. That's just v0x, right? This was really, whoops, v0x is always on the left, and v0y, okay, times the time, and we'll call that, let's do it t with a capital F for final. Yeah, trying to save space now. Okay, but what is that final time? How do I know when it lands? Right? The x information is never going to tell me that because there's no acceleration. It just continues on at a constant speed until whatever. What determines when it stops is happening in the y direction. So to get TF, I have to set delta y equals 0, and that equals v0y plus 1 half ay t final, oh, v0t, t final squared. Okay, so there I have my equations. I'm really going to exploit this 0, okay, but I'm going to plug in for v0y, move it to the other side, so minus v0 sine of theta, theta is my 30 degrees, times t final equals, we can really put in g for ay, equals minus g over 2 t final squared. You might think, oh dear, a quadratic. Did I mess it up? Okay, I'm trying. Okay, good. But aha, let's divide both sides. I know, my algebra just runs on and on and on. Let's divide by negative t final. Oh, v0 sine theta equals g over 2 times t final. So t final is just 2 v0 sine theta over g. Sine theta was a half, so that gets rid of my 2 v0 itself is 20. Yes. And g is 10. The the 2 came from the 1 half at squared. Okay. So, whoops, we're just going to plug in. It should take 2.00 seconds to hit the ground. Okay. Now, why ever did we do this madness? It's because you have a homework problem coming up. Maybe you like working in algebra, and that's fantastic. Sure. Well, being lazy. Notice how the negative signs disappeared on both sides. Okay, good. Okay. Oh, so then your max range, it would be to take this 2v0 sine theta, times r. Fantastic. I'm making one of those homework problems really easy for you. Like problem 49, it says derive this for the range of any projectile on the ground. Okay, well look, that's why I might want to do it this way, so I proved it. I mostly just did the problem there for you. Okay, it doesn't have any initial conditions, so you just have to deal with v0x, v0y. There's sines and cosines all over the place. So I mostly did 49, and I brought this up because there's an identity that you may not know from trig, that if you have 2 times the sine of an angle times the cosine of the same angle, can you kind of see how that's going to happen up here? If I plug in t final right here to solve for the range, whoops, which should actually be 34.6 meters. That's my final answer. Okay, in this case, 2 times sine times cosine of the same angle equals sine of double that angle. And that 2 theta is in parentheses there. To simplify and derive all the way, that's the famous range formula. In freshman physics class at Purdue, they really encouraged us to memorize the range formula to use on tests or to check our answers. They didn't give us equation sheets. They thought that was funny. Even though College Board, evil College Board still gives equation sheets. And Purdue, they said, no, memorize it, because they're trying to make it as hard as possible. But I knew how to plug everything in, so why memorize that? Sine times cosine might actually be easier. And if you can see how it comes out in the formulas, it's easier to check your work. But you'll need that identity to complete the proof on the homework. Okay. Any questions? You can dispute my answers. I always like that. Okay. So, see how, maybe I should insert a page. Are you imagining now how we have v0x and v0y, and then only y has an acceleration term? Like when I go to calculate the next row, I think it's not super obvious how I've written it that way. Okay. You ready to try one more? And then you can have homework time? Sure. I got my 2 seconds as t final here, and then I multiplied 7.3 or 17.3 times 2. And I think I multiplied right. It's really, so it's 20 times the cosine of 30 times 2 seconds. Did I mess it up? No. What do you think, Landon? It's okay. Okay. Right, there's always this balance going on in my mind. I want you to have more homework time so you can get mostly done, but I don't want to leave out something critical so then half the people are stuck. Okay, so I'm going to try to do this next example in a specific way. Okay, we have a small airplane flying. Don't fly in hurricane force winds, by the way. 60 meters per second is awfully fast. That's over 100 miles an hour, I think. Meters per second, not kilometers per hour, meters per second. Okay? So, here's what's going on. The airplane points itself due west, and we're due VPA for plane through the air. If you like these little subscripts, then go ahead and carry on. If you don't, then that's okay. But VPA is 80 to the west, and then we have nose to tail. There's the wind. There's the velocity of air relative to the Earth going north, and it's 60. Okay. In my silly vector notation, I would say like VPA is negative 80 in the x direction, because we try to fly due west, and 0 in the y, and then V air to the earth is going 0x, and it's going 60 up in the y direction. Oh. So I like to write them in like a little table, like it's a giant addition problem. Okay, or you could actually make a table if you feel like it. So then the vector sum, velocity of the plane relative to the earth, try not to accidentally spell something bad, vape, almost. Okay, so there's its x and y components, but that is just the hypotenuse of this triangle. And oh look, it's a 3, 4, 5 triangle. Okay, and you could do Pythagorean theorem, right? We would call it the result, or you could call it C, is the square root of 80 squared plus 60 squared. And that's my 100. Okay? So, if I want a vector velocity, I could actually put negative 80 plus 60 with a comma in between, like an x, y coordinates. And I always remember the angle brackets, like on a test, it would show up that way. But if you just remember that's x comma y, that's good enough. Okay, and then it's just a triangle. So there you go. And this is our trusty, so you could describe this as like 37 degrees north of west. Or you could describe it like, what's that, 143 degrees from east. Like if we go north, south, east, west, then our physics convention of measuring everything from x or east becomes really clunky. But you know what? It's reasonable. I have to accept those answers. So when you get a bunch of vectors, like in those first few problems, split them into x and y, just like we took v0 at 30 degrees and we split it into x and y. Split everything into x and y, add x's to x's and y's to y's, and then if it just asks for a vector, guess what? That's a vector, x comma y, with pluses and minuses, hopefully with my angle brackets, make it look nice. That's a vector, you're done. If they ask for a vector, no problem. If they ask for the magnitude of the speed or something, then you might actually have to go full blast, do Pythagoras' stolen theorem, and figure out that it's 100 on that side. Or you can do, you know how to use trig. Like if I didn't know this angle, if it was something weird, you could do sine, cosine, tangent to get either one, and you could get it. Yes, that's easy trig, or you're not that far. Landon's not that far. Okay. The easiest way, thanks Landon, he's not ashamed. Okay. If we want that angle there, that's 37, tangent of this angle is y over x. So we got velocities here. That would be, it's always vy over vx. Does that appear on your equation sheet? Okay. And then so this angle, that's theta, in your calculator you would do, I think its fancy name is arctan, or inverse tangent, of 60 over 80. It's always the y over the x. Try it, and it will tell you. Make sure it's in degrees. I like my little cheap ones because it has a little, it always says right there at the front, degrees or radians. Okay, some of them do radians by default. That's bad. Okay, we'll do degrees, and it should say 36.87. Okay? Alright, well I want you to have more than half an hour, almost 40 minutes now, I think. Yeah. Okay, try all the problems, I'll leave this up, just break the vectors down. I'm going to come around and look over your shoulder and see that you have notes up to this point. And that's your notes check. Oh, I have to unpause it to stop my video.